Alright, so we've been talking about the periodic table, and we will get back to the periodic table. But this unit is not only about the periodic table, it's also about the structure of the atom. So in terms of the structure of the atom, we're going to look at nuclear radiation. Okay? Part of this unit includes some discussion and understanding of nuclear radiation. Now, I want to first kind of give you kind of an overview of what some of the terms we're talking about here. Nuclear decay. Nuclear decay. If it says nuclear in front of it, that means it's happening where? In the nucleus. Okay, now this is the nucleus of the atom, not the nucleus of a cell. Okay, the nucleus of the atom. The nucleus of the atom has two kinds of particles. Now, if you get underneath that, you know, get into high-level physics and stuff, you find out even those particles are made of other particles. But what are the two particles in the nucleus of an atom? Not electrons. Protons and neutrons are in the nucleus, okay? So if the protons and neutrons break out, or if the protons or neutrons themselves break up, then you've got decay. Alright? Decay just means it's kind of breaking down. Does that make sense? Now that's not the same thing as splitting the atom. You've probably heard that term before. Splitting the atom is something else. Decay means it's small parts kind of coming apart, okay? Nuclear decay is when you are breaking up the nucleus in some small fashion. You're breaking up some small part of the nucleus, okay? Things are coming out of the nucleus. You might say nuclear decay means things are coming out of the nucleus. Okay? Wait, what did you say about breaking up? If we could refer to nuclear decay as things coming out of the nucleus. N-U-C-L-E-U-S. Nucleus. Nuclear is N-U-C-L-E-A-R. Nucleus. Nucleus is N-U-C-L-E-U-S. So nuclear, N-U-C-L-E-A-R, decay, means that things are coming out of the nucleus, N-U-C-L-E-U-S. Okay? Now, if we have nuclear decay, there's different types of nuclear decay. And we'll get into that more a little bit later. There are different types of nuclear decay. There are lots of them, but we only know about 3 of them in high school. Okay, we're going to talk about all 3 of those later today. Right now we're going to kind of stay on a bigger plane of understanding here. But whatever kind of nuclear decay you have, that decay is what's happening in the nucleus. The nucleus itself is kind of breaking apart a little bit. Just tiny little bits of it breaking apart. Not the whole thing breaking apart, just little pieces, okay? And when those little pieces come out of the nucleus, then you have emission. So nuclear emission means those particles are coming out of the nucleus. Okay? Nuclear decay means something's kind of breaking down. Nuclear emission means it's coming out. Does that make sense?
So decay means breaking out of nucleus, not coming out.
Right. Kind of breaking up is nuclear decay. Coming out is nuclear emission. What?
You said coming out.
Well, okay. Nuclear decay is kind of things. It's coming out. When it comes out, it's emission. Okay?
So what I need to change?
No, nuclear emission is when it actually comes out. So if we're getting stuff out of the nucleus, that's emission. Okay? And it'd be even if we want to be really, really picky and specific about it, it's coming out of the atom itself. But you know, let's not. Most of the electron cloud's empty space. If it comes out of the nucleus, it's going to come out of the atom for the most part. Although some things don't all the time. Okay? Most of them do. Now, once we have emission, then the combined effect of all those particles or all that energy coming out is what we call radiation. So once it leaves the atom altogether, or a bunch of atoms altogether, then we have radiation. All right, you getting kind of the idea? This is happening in the nucleus. This is what happens when it leaves the nucleus. This is what happens when it leaves the atom. Got it? When it's out here where we are, we call it radiation. Okay? Yeah. It's really anything, but in terms of nuclear radiation, it's when it comes out of the atom. You can think of it that way, okay? But there's all kinds of radiation. There's radiation coming out of the lights in the ceiling right now. Okay? There's even radiation coming out of the walls. There's radiation everywhere. Okay? If there's light, there's radiation. Okay? But there's other kinds of radiation. And some of those types of radiation are actually particles. But it brings me to the term, did we discuss isotopes yesterday?
Yeah.
Okay, so I told you what isotopes are. Okay? So isotopes then are different forms of the same element, and the different forms of the same element are different because they have different numbers of neutrons. Okay, so there's carbon-12, which has 6 neutrons. Isotopes are different forms of the same element. Atoms of the same element that are somehow different, and they're different because they have different numbers of neutrons. Different forms of the same element differing in the number of neutrons, which by extension means they also differ in mass, because the weight of the nucleus is protons plus neutrons. So atomic mass is protons plus neutrons. All right? Okay. Now, every element has different isotopes. Every element has different isotopes. There's no element that doesn't have different isotopes, okay? Some of those isotopes are radioactive, meaning they're unstable. They're breaking apart. They're decaying. If they're going through decay, they're emitting particles or energy. If they're emitting particles or energy, we get radiation from them. Okay? So, all elements have some isotopes that are radioactive, that emit particles, that are going through decay. Most elements have at least some stable isotopes. Most elements have at least some stable isotopes. So, elements from 1, hydrogen, up through 83, bismuth, have some stable isotopes. Maybe only one, maybe more than one. Beyond bismuth, there are no stable isotopes of any of those other elements. Beyond bismuth, there are no stable isotopes of any of those elements. So polonium has no stable isotopes. Astatine has no stable isotopes, and so forth. So, 83 is bismuth. B-I-S-M-U-T-H. But you have a periodic table. I gave it to you yesterday. It involves you actually getting out of your ring binder? Imagine that.
Yeah, it involves words.
Get it out! My gosh!
Look at this right here.
There you go. Look at that. All right.
There's no other stable words.
Beyond bismuth, beyond element 83, there are no longer any stable isotopes of any of those elements.
You did give them. Oh, that's two.
Oh, imagine that. I did give it to you. Wow. Get out of here. Okay. So anybody listening to the audio here? We're just playing around. What? Yes. Oh, you got to have one too? All right. Y'all help me out and pass this back to him, okay? Thank you. Now, if you guys, what I suggested people do that yesterday, what I suggested with people do with that yesterday, is that you staple it so they stay together, and then you hole punch it and put it in your ring binder. Okay, and the stapler and the hole puncher up here. All right, now, so if there are no stable isotopes of any of the elements beyond 83, what do we know about uranium?
Nothing.
We know it's what?
Radioactive.
It's radioactive. It has to be, because beyond 83, there are no stable isotopes, and uranium is beyond 83. Okay? So uranium is going to be radioactive. And what we're going to be seeing today in the cloud chamber is evidence of that radioactivity.
Are you going to get radiation poison?
No. But that brings up a really interesting question, because a lot of students are scared by the word radiation. Okay? And it's even more scary when I say it, radiation. All right. Look, I said this in the beginning of class. There's radiation in this room right now. There's gamma radiation coming out of these concrete walls. But listen, there's so little of it, it's not going to hurt you. The amount of radiation you're going to get from this low-grade ore in this cloud chamber lab is so small, you get more radiation walking down the hallways with the concrete walls. Okay?
You get more with concrete?
In a day at Darwin High School, you'll get more radiation exposure, gamma radiation exposure, from the concrete walls than you will from this little low-grade piece of ore.
You know why?
Can we just stay on this topic right now? Is your question about this topic? Okay, well, let's hold your thought just a little bit, okay? All right. So, all we're going to do is just observe. All right? You've got your cloud chamber set up. We're ready to go observe. Now, that means that in your cloud chamber, everybody has a cloud chamber that looks something like this. What you want to do is to shine your flashlight kind of at an angle. All right, so that you get what you want to do is be able to get the light at an angle like this. All right, and then you're going to be looking at it from a different angle. Now the light needs to shine kind of down so you can see around your piece of ore in the bottom. Okay, and you're going to be looking at it from another angle, so you're going to see that little halo of light around that rock, and you're going to look for anything out of the ordinary. Patience. Patience. Good observations. Yes, in this case, patience is definitely a virtue. That's up to you. I think this picture in your lab notebook would be fabulous. Now, hold on one second. Patience. Constant, determined observations. Got it? And look for anything out of the ordinary. Everybody ready? Yes, what's your question? Virtue is a good thing. Yes. What? Oh no! That's not good. If it needs to sit on top of the dry ice to form the cloud. Go do it quick. We're ready to start anyway, so everybody go. Let's go. Yes.